Welcome to brilliantmaths.com, where every student has an opportunity to excel in math. Have you subscribed to brilliantmaths.com yet? Please do so. We have lots and lots of resources for you. We have modules that cover primary and secondary school mathematics. We have video lessons, and we also have virtual lessons that you can participate in. So go to brilliantmaths.com and be one of our students. Today, our lesson is taken from Module 1, Brilliant Maths Module 1, Approximations and Limits of Accuracy. Rounding whole numbers. We want to round 6,543,789 to the nearest 10, 100, 1,000, 10,000, 100,000, and million. And how do we do that? To round a number to the nearest 10, you look at the unit column. If the unit number is 5 or more, you round up. You round up by adding 1 to the number in the tens column. If it's less than 5, you round down. You round down by leaving the number the way it is and rounding the unit number to 0. So 6,543,789 to the nearest 10 is actually 6,543,790. We all know that 89 is closer to 90 than to 80. Good. We want to round 6,543,789 to the nearest 100. 789 is closer to 800 than to 700. So we can look at the last 3 digits and find out which 100 it's closer to. So 789 is between 700 and 800, but it's actually closer to 800 than to 700. Another way is look at the tens column. If the digit in the tens column is 5 or more, you round up. So you round up by adding 1 to the 7 and it becomes 8, and then round down if it is less than 5. So 6,543,789 to the nearest 100 is actually 6,543,800. We want to round the same number to the nearest 1,000. The 1,000 column is a 3. So we can simply follow the same process. If it's a 3, look at the digit in the 100 column. It's 7, so it's more than 5, so we can round up. And it becomes 4. We're adding 1 to the 3 to make it 4. So it becomes 6,544,000. Another way is to look at the last 3 digits, 789. If the last 3 digits is more than 500, because 500 is half of 1,000, then you round up. If it's less than 500, you round down. So since 789 is greater than 500, which is half of 1,000, we round up so that the answer becomes 6,544,000. And the rest digits go down to 0. We must write the zeros there because the number is a whole number. There are 0 placeholders. Rounding to the nearest 10,000. Where is the 10,000 digits? It's a 4. So we look at the digit before the 10,000, and that is 1,000 digits, and that is 3. And 3 is less than 5, so we round down. So the answer becomes 6,540,000 to the nearest 10,000. Anytime you're rounding, you must come back to the original number. So we go back there to round to the nearest 100,000. The 100,000 digit is 5. But you have to look at the digit before it, which is a 4. And that is less than 5. So we also round down. So to the nearest 100,000, it becomes 6,500,000. And as you can see, 543,000 is closer to 500,000 down to 600,000, if you put it in that scale. And for the last one, we're rounding to the nearest million. The digit there is 6. 6,543,789. 543,000 is more than halfway between 6 million and 7 million. So it rounds up to 7 million. Or you could say the next digit is a 5. And when the digit is 5 or more, you round up. And you round up by adding 1 to the digit you are rounding. So it becomes 7 million. So if 6,543,789 is rounded to the nearest million, the answer is 7 million. Here we want to learn how to round decimal numbers to the nearest tenth, or to the nearest whole number, the nearest hundredth, thousandth, and so on. But the first thing we should know is rounding numbers to the nearest tenth is the same as rounding the number to 1 decimal place, because the place value of the first digit after the decimal point is tenth. So that's rounding numbers to 1 decimal place. 2 decimal places is the same as rounding to the nearest hundredth. Rounding to 3 decimal places is the same as rounding to the nearest thousandth. It's good for us to understand that vocabulary so we can apply it. Example 1. Round 0.3746 to the nearest tenth. So we're rounding to the nearest tenth. That is, we want to write only 1 digit after the decimal point. So we look at the second digit, or rather the next digit to it, and it's 7. 7 is more than 5. It's more than halfway. So we round up. So it becomes 0.4. We round up by adding 1 to the 3. And then the rest numbers will go to 0 because they are no longer significant. These are numbers after the decimal point. They are fractions. This number is actually less than 1. That's why we call it 0.3746 and not 0.3746. All the digits after the decimal point are called 1 by 1 because they all stand alone. They are all fractions. 3/10, 7/100, 4/1,000, and 6/10,000. Rounding to the nearest hundredth, or to 2 decimal places, we have 7 in the second decimal place. The next digit to it is a 4, so it's less than 5. So that's easy. We're rounding down. 0.37. Rounding to the nearest whole number. Nearest whole number. The unit digit is 0. And the digit after the decimal point in the 10th place is 3, which is less than 5. So this number to the nearest whole number is actually 0. 0.3746 is closer to 0 than to 1. It's actually less than halfway. Halfway 0 and 1 is 0.5. So since it's less than half of 1, the answer is 0. Then we round to the nearest thousand. So this is thousandth, remember? All the decimal numbers have TH. When we're rounding to the nearest tenth, it has a TH. Hundredth, thousandth, that shows that they are decimal numbers. Tenth, hundredth, thousandth, but we have to look at the next digit, which is a 6. It's more than 5, so we round up. So the answer is 0.375. Round up by adding 1 to the 4. In example 2, we're rounding 8.3956 to the nearest whole number. Nearest whole number, the whole number is 8, and the first digit after the decimal point is 3. So, to the nearest whole number is 8, because 3 is less than 5. To the nearest 10, the unit digit is 8, and 8 is more than 5. 5 is half of 10. So to the nearest 10, it is 10. 8 is closer to 10 than to 1, if we're counting in tens. Round to 1 decimal place. 1 decimal place means the 10th column. That's a 9 after the 10th column. So the answer becomes 8.4. We round up. Because we have a 9, we're adding 1 to the 3. To 2 decimal places. 9 is in the second decimal place, and 5 is the next digit. So we add 1 to the 9 to round up, and then that becomes a 0, and we have 4. So the answer is 8.40. This 0 is significant. You must write it because we want to write 2 numbers after the decimal point. If you write the 0, if you write anything else here, your answer will be wrong because you want only 1 number after the decimal point. That's why it says 1 decimal place. Then 3 decimal places for the same number. 8.3956. 3 decimal places, we had 5. And the next digit is a 6. So we simply round up by adding 1 to the 5. And our answer is 8.396. This is very easy. Take time to look at it again. Next, we want to round to significant figures. Round 48,599 to 1 significant figure. We want only 1 significant figure, so we are rounding to the highest place value. And the highest place value here is tens of thousands. So 48,599. You look at the digits, the next digit to the 4 is an 8. So it's greater than 5, so we round up. But basically, we're saying 48,599, if you are counting in tens of thousands, is between 40,000 and 50,000. So is it closer to 40,000 or to 50,000? But we know that 48,000 is closer to 50,000. So this rounds to 50,000 to 1 significant figure. This is the whole number. So you must write the zeros as placeholders. You can't discard them like you do in decimals. To 2 significant figures, 4, 8. 8 is the second significant figure. But before you round, look at the third one. The third one is a 5. It's halfway. So we round up. So it's approximately 49,000. So we are saying 48,599 is between 48,000 and 49,000 if you are counting in thousands. But because it's more than halfway, we round up. And the last one in this example, we're rounding to 3 significant figures. 1, 2, 3. The next digit is a 9, so we're also rounding up. So it's 48,600. So basically, we're saying that 48,599 is closer to 48,600 than to 48,500. In the next example, We're rounding 0.04963 to one significant figure. In the case of decimals, any zeros immediately after the decimal point are not significant until the first non-zero digit. So this 0 is not significant. Ordinarily, somebody will look at it and say, first significant figure, one significant figure, so it's 0. No, it's not. This 0 is not significant. So to one significant figure, that number is 0.05. Because 4 is the first significant figure, and the next digit is a 9. So 4 plus 1. And then we discard the rest, because like we said, these are decimals, so they are no longer significant. Two significant figures, 1, 2, 4, 9. Before you write the 9, check the next one. It's a 6, so you're rounding up. So you need to add 1 to the 9, and it becomes 10. So the answer to two significant figures is 0.050. You must write that 0 there, because it's significant. We have added a 1 to the 9 to make it 0. Please take note of that. That's very important. For the third example, we're rounding to 3 significant figures. So the answer becomes 0.123049. The third digit is a 6, and this is a 3. So what is it going to be? 0.496. Because 3 is less than 5, so we're rounding down. Please take your time to study this and understand it, because it's a very important concept. And it's also very easy, as you can see. Here we want to look at limits of accuracy. Limits of accuracy. Look at these numbers, 3.5, 3.50, 3.500. They all appear to be the same. But in the real sense of it, they are not. They are not because the numbers have been rounded to different decimal places. This first one, 3.5, has been rounded to 1 decimal place. And this has been rounded to 2 decimal places. And this has been rounded to 3 decimal places. And there's so many numbers that can be rounded to 3.5. So for example, in a hospital, 2 women give birth to newborn babies. And one of them weighs 3.54 kilograms. And they record the birth weight to 1 decimal place. So this will be rounded to 3.5 kg. The second woman's baby weighs 3.49 kilograms to 2 decimal places. But the birth weight is recorded to 1 decimal place. And that's also written as 3.5 kilograms. But the actual weight of the 2 babies are different. So that's why we'll be looking at limits of accuracy. And talking about limits of accuracy, you'll have to define upper bound and lower bound. And what do we mean by upper bound and lower bound? What is the highest number that could have rounded to give us 3.5? That would be the upper bound. And then what is the lowest number that could round to give us 3.5? And that would be the lower bound. Upper bound is greater than lower bound. So for this particular weight, 3.5 as we're looking at, if another baby weighs 3.56 kilograms, would that round to 3.5? No. This would round to 3.6. So that is out. Anything higher than 3.54 would not be part of that bracket. Let's look at the lowest limit. So obviously, the highest limit we have is 3.54. But for convenience of writing, it is usually written as an inequality. And the upper bound inequality is a strict one. It will be strictly less than 3.55. So for the lower band, 3.49 would round to 3.5. 3.48 would round to 3.5. And down all the way to 3.45 kg. This will still round to 3.5. You agree with me? But anything less than 3.45, for example, 3.44, would not round to 3.5. So the lower bound is actually 3.45. So that will be written as an inequality, 3.45 being the lower bound, and then 3.55 being the upper bound. Let's look at it here. So write the upper bound and lower bound of 3.5. Solution. Like we said, upper bound and lower bound is usually written as an inequality. So the lower bound is 3.45. That is lower bound. And then the upper bound is 3.55 for convenience of writing. And then it is written as, so our number is actually S. Let the number 3.5 be X. So the upper bound and lower bound will be written as 3.45 less than or equal to X. That means 3.5 is greater than or equal to 3.45. So 3.45 is inclusive. And X is strictly less than 3.55. Another way this can be explained is to find the upper bound and the lower bound, look at the number of places it's been rounded. It's been rounded to the tenths, to one decimal place. So you find half of tenth. Half of a tenth is 0.05. You find half of a tenth and add it and subtract. You add it to get your upper bound. So 0.05 plus 3.5 will give you 3.55, which is our upper bound. And if you subtract, let's do that one, 3.5 minus 0.05, that will give us 3.45. And that is our lower bound. So to find the upper bound and lower bound, find half of the place value that that number has been rounded to, and then add and subtract to the number to find the upper bound and the lower bound. We'll take more examples. We want to look at upper bounds and lower bounds, but actually looking at absolute error. How to actually find upper bound and lower bound of values that we have. Absolute error is the magnitude of the difference between the exact value and the approximation. Remember, we mentioned that if you have a number rounded, there are several other numbers that could have rounded, exact values that could have rounded to that number. So for example, 3.50 has been rounded to 2 decimal places. So we had a number, let's say 3.54. And it was rounded to 2 decimal places to give us 3.50. And 2 decimal places is the same as nearest hundredth, like we know. We want to find the upper and lower bound of 3.50. What is the least number that could have been rounded to give us 3.50? And what is the highest number that could have rounded to give us 3.50? Absolute error is the difference between that exact value and this approximation. And the absolute error is found by dividing the place value that has been rounded to by 2. Finding half of that place value, that's the absolute error. So we add that absolute error to the value to give us the upper bound, and we subtract the absolute error from the value to give us the lower bound. So for example here, 3.50 is been rounded to the nearest hundredth. So our absolute value is half of 0.01, which is 0.005. So we're saying absolute error equals half of a hundredth, which is equal to 0.005. So our lower bound will be equal to 3.50 plus 0.005. And that gives us 3.505. And then our upper bound, sorry, that's lower bound, so we're supposed to be subtracting. So it means 3.50 take away 0.005. We need a 0 there, so we can borrow. So 10 take away 5 is a 5. And then here, we have a 9. I hope you know that. 9, and then we have a 4. So our lower bound is 3.495. 3.495 will round to 3.5 if you're rounding to 2 decimal places. And then our upper bound will be equal to 3.50 plus the absolute error, 0.005, and that's 3.505. So our lower bound is 3.495, and our upper bound is 3.505. So we write it as 3.495 is less than or equal to x, which is our value, our rounded value, and that is strictly less than 3.505. Because 3.505 on its own will round to 3.51. So it's strictly less. And that number is usually 3.5049 something. But it must be less than 5. This is very tricky. You can find a lot of it and more explanation in Brilliant Maths Module 1. So assuming the number was rounded to the nearest whole number, say 7, find the upper bound and the lower bound. The absolute error is half of 1 because it's been rounded to the nearest whole number, and the whole number is 1, right? Half of 1 is 0.5. So the upper bound will be 0.5 plus 7, which will give us 7.5. And the lower bound will be 7 minus 0.5, which will be 6.5. So it will be written as 6.5 is less than or equal to x, which is strictly less than 7.5. Get Brilliant Maths Module 1. You would really find it very useful. We want to look at a problem involving upper bound and lower bound. Please pay attention. It can be a little tricky. A car travels 40 meters measured to one significant figure at a speed of 2 meters per second measured to one significant figure. Find the upper and lower bounds of the time taken. The distance the car traveled has been approximated to one significant figure. and the place value of that figure is 10. Take note of that. So the distance is 40. So that means that the absolute error will be half of 10. Do you understand that? The absolute error will be half of 10. So to find the upper band and lower band of the distance, we'll be adding and subtracting half of 10, which is 5. So the upper band of the distance will be 45 meters, and the lower band of the distance will be 35 meters. I know you get that. The speed is also approximated to one significant figure. The place value is 1 unit, and half of 1 is 0.5. So to find the upper band and lower band of the speed, we'll be adding and subtracting the absolute error. So we have 2.5 and 1.5 as our upper band and lower band. I wanted you to get that. Good. So to find the upper band and lower band of the time taken, solution, the distance traveled is 40 meters, rounded to one significant figure. The speed is also 2 meters per second, rounded to one significant figure. Time is distance divided by speed. So the time taken is the distance over the speed. But when it comes to division, finding upper band and lower band, solving problems. When it comes to problems involving upper band and lower bands, and you're supposed to divide, you don't simply divide the upper band of the numerator by the upper band of the denominator to find the upper band. No, there's a rule. The rule is you divide the upper band of the numerator by the lower band of the denominator to get the upper band of that division. And then to get the lower band of the division, you divide the lower band of the numerator by the upper band of the denominator. And 40 meters, remember it was to one significant figure, and we have said earlier that the significant figure there is, the place value is 10. So the absolute error is half of 10, and half of 10 is 5. So that's why we have our lower band to be 40 minus 5, 35, and our upper band is 40 plus 5, 45. So 40 meters lies in that range. And also, 2 meters was rounded to one significant figure, and half of 1 is 0.5. So 2 plus 0.5 gives us 2.5 as our upper band, and 2 minus 0.5 gives us 1.5 as our lower band. So now, the upper band of the time taken, which is this division, will be 45, the upper band of the distance, divided by 1.5, the lower band of the time. That will give us the upper band of the time taken. And then the lower band of the time taken will be 35, the lower band of the distance, divided by 2.5, which is the upper band of the time taken. So 45 divided by 1.5 gives us 30, and 35 divided by 2.5 gives us 14. So let x represent the time taken. If x represents the time taken, the upper band and the lower band will be written as 14 less than or equal to x, which is the time taken, and then it's strictly less than 30. So we have been able to find the upper band and the lower bands of the time taken. Get a Brilliant Maths Module 1. You'll find lots of this in it, and it will help you to understand it better. Again, subscribe to brilliantmaths.com. The modules come with examples, exercises, video lessons, and answers to help you check your work. I am Ngozi Forever. Always, always remember, maths is fun easy. And you